Hello, everyone. Thanks for coming to my talk. My name is Sam Pollard, and I'm going to be talking about research with Boyana Norris, my advisor at the University of Oregon. And the topic is a statistical analysis of error in MPI reduction operations. I'm going to start by giving a motivation and an overview of floating point arithmetic. So floating point arithmetic, as we all might know, is not associative. If we define a plus with a circle around it, I'll be using this throughout the talk to be floating point addition, we can find some simple examples where the results are not equal, but these are only not equal at the last bit. It is much more interesting when we have, and when worse, when the error is greater, and this happens when the magnitudes of the two or three summands are much different. So we see here what is known as catastrophic cancellation between B and C. So depending on how you order a result, which in real arithmetic is just 1, it can be 0. This brings up the question, what is the effect of assuming associativity for parallel summation error? And specifically, how does this affect MPI, the message passing interface, and its reduce operation? Put a little more formally, we can bound the relative error. If we have op be a binary operation, add, subtract, divide, or multiply, this works similarly for square root, and we'll call it dot be its corresponding floating point operation, then x op y in its real arithmetic is bounded by epsilon. Its relative error is bounded by epsilon. Now this holds only when x and y are non-zero, as well as normal floating point numbers, that is not subnormal. This assumption is suitable for our purposes, but we will see examples and describe a little bit the effects of subnormal arithmetic. Throughout this presentation, we'll be using double precision arithmetic, floats, and in this case, epsilon is 2 to the negative 53. So first I'm going to talk about a little bit about how MPI works and its reduction, specifically associated with its reduction operation. Throughout the example, we'll have an array of size n, array A, and MPI reduce works by repeatedly applying a binary operation to A until a single value is reached. The interesting ones here are MPI sum and MPI product because they are non-associative. Essentially what we're doing here is distributing A across its ranks. We see each piece of K. Now there is an unspecified but typically deterministic reduction order when run on the same architecture and topology. What that means is popular implementations like OpenMPI, impitch, will result in the same answer. But if you have something like a different partition, or rather a different allocation on a supercomputer, you might get a different answer. Or run at a different level of parallelism, you might get a different answer. These sorts of questions we want to investigate of something like how bad can the error get when we run on different architectures. So to answer this question, the next question we want to ask is, how many ways are there to do this MPI reduction? The answer, well, it depends, is the answer. We are going to list 4 families, and these 4 families are depending on the problem scope. The first one is the serial implementation, maybe the simplest way to add up an array of numbers, where you just left associatively add them. It's unambiguous, there's one reduction strategy, but there's no freedom to exploit parallelism. So this is a problem because the whole reason MPI exists is for parallel computing. So to look at parallelism, we begin with the MPI standard. The MPI standard is very flexible. It assumes some binary operation op, as we've denoted before. It's associative and commutative. So the implementation can take advantage of this, and that will result in different answers sometimes. So this is a little bit complex to describe, so let's start with another permittable MPI standard, which is the case if you have a custom operation and you require commutativity of this custom operation. In this case, the order of the operations is fixed and you have ascending order, starting with process 0. The association can be changed, however. That's how we get to parallelism. So in this case, let's call it the commute false case. We're going to have a fixed order and a random association of operating on these values. What this means is we have a tree that we're traversing in order, a binary tree, and combinatorially describing the state space of these trees is a catalan number, right? There are an array of size n, or a binary tree with n nodes, or rather, n leaf nodes. There are Cn, there's the Catalan number of different combinations. We're going to call these associations, but essentially just remember we're dealing with binary trees here, but associations for notational convenience. One example summation here with floating point arithmetic is this case where R1 is equal to R2. We can exploit commutativity to get the same result. You can apply commutativity to B and C and then to the outer expression. However, it is not the case that R2 is equal to R3. We can see this because we would, in order to do this, we need to rearrange the tree, and that is not permissible under non-associativity. So to completely describe the default case, or what happens when you call MPI reduce, we have random order and random association. Neither of those are specified. And because of floating point associativity, because of floating point commutativity, there are fewer than the Catalan number of different results that can arise. Now, this is a less well-known, but a still solved combinatorial problem where for an array of size n, there are g sub n different solutions. In this case, 2 exclamation marks is the double factorial on odd integers, and this is the product of all odd numbers up to 2n minus 3. So that's the third case, the third family. We want to talk about the fourth family, which we call random order left associative. This is done if we were to generate these by shuffling the array first and then summing canonically, so summing in a left associative way. This is not exactly part of the MPI standard, but its main purpose is to compare it with previous work by Dylan Chapp and others. And they use this when generating various different results for floating point summation. So we compare here. Next, we're going to talk about how we actually generated these random binary trees. Again, this is a solved problem using Remy's procedure from as described in Donald Knuth's Art of Computer Programming. Given a tree with n-1 leaf nodes, this is a nice iterative algorithm, and you pick one of the nodes randomly, and this node x can either be a leaf or an interior node, and you add a new node k in one of two ways. You add a new leaf by either, I guess, to the left or to the right, and then you connect accordingly. So doing so can produce all binary trees of order n. And when I say order n, I mean n leaf nodes, which is great because that is exactly the state space that we described with random associations. Now that we've talked about the state space, we're going to go back into floating point arithmetic a little bit and talk about some analytical balance. If we have a floating point sum, which is sigma with an O plus around it, or on top of it, and S sub A be the true sum, in 1963 there was already, this is far before IEEE floating point arithmetic, but there's already been a lot of analysis on floating point arithmetic. There's summation error had been bounded by this term on the right. So we have the error of summation on the left is less than or equal to epsilon times the size of the array times the relative magnitudes of, or the absolute magnitudes of each element, with an additional epsilon squared term, which can be ignored usually because it's much smaller. And as it turns out, this equation 2, this bound is very loose. It assumes that all of the error are as bad as they can be, which works in some pathological cases, but we want to investigate what happens in the average case. Because this bound is so loose, there have been further estimators and ways to guess the bound in a more realistic way, but they require some stronger assumptions about the input. So supposing you have this array A, and each of the elements are positive and distributed either uniformly or exponentially. This is the first assumption. The second assumption is that floating point errors are independent and distributed with mean 0 and some variance. It doesn't make an assumption about what the distribution is, just that they have mean 0 and variance sigma squared. And 3, the summation ordering is random, which is great for us because that, again, we have random ordering and random association for our state space. In that case, the error is approximately equation 3, and we'll plug in values for this later, so don't worry too much about the details. But this does tend to be a tighter bound than Wilkinson's bound. So now we'll talk about empirical results. Here, there's kind of a lot going on. So I'll talk about, let's notice the bottom right here. We'll talk about the problem as the experimental domain as we described it. There are uniform 0, 1 distribution, each element in the array. The array is of size 2 million, and there are 50,000 trials. So these 50,000 trials make a histogram, which is the y-axis, right, the count. The x-axis is the difference between a high precision value and the computed sum. So we used a 1,000 digit MPFR, multi-precision floating point library, to compute the true sum, and we just took the difference, so we can actually see the result is biased here, and in some cases, right? So ROLA is, recall, the random order left associativity is more biased than random order random associativity. Now this is because as you are adding up an array, left associative, you have a running total, a running sum, which is much greater than these number added to it. So this is how we get underestimating the true sum, is because we're losing a lot of some bits on the small end of the mantissa. Another interesting thing to note, so RORA is much better, and what we see here is that the worst case of RORA, and it's not labeled here, but we'll see it tabulated, is actually better than the canonical sum, and the canonical sum is that dashed, dotted and dashed blue line. So this is interesting because it says in some cases the MPI state space, so randomly summing and associating, can be better than the serial implementation. Another thing is we see the red graph, the RORA, is copied over here, except for we measure the absolute error instead of just the difference here. And we do this to show that fixed order random association is about the same as random order random association. This is not too surprising for two reasons. For one, we have commutativity of floating point arithmetic. And for two, the error from summation mainly arises from adding small numbers to large numbers, or right where the magnitudes are very different. Another thing to note is that the canonical left associative would be off this chart, but it is in the previous chart. So we can see it's about on the order of 5 or 6 to the -9, and this chart only goes to like 3 to the -10. Again, so let's talk about RORA, but with different distributions this time. We use relative error here because they are all different distributions, so the magnitude ends up being much greater, right, for the uniform -1,000, 1,000. So we use relative error to measure them all in the same graph. And the uniform -1, 1 is greater because we have these catastrophic cancellations. So what we result in is some cases there's a there's a number in almost its inverse added together to make a number close to 0, and that exposes a lot of the lower order bits where error comes from. Another thing to note is the sub n there. That is a distribution that generates subnormal numbers on average. So the error is not as bad as one would originally think because the running sum is so small. The partial sum does not end up being particularly large, so that we don't get as much of this magnitude differences. As well as we can see the uniform 0, 1 is also rather low. So we're going to focus on the uniform 0, 1 results tabulated, and notice the bar is the average overall results. And a few things of interest here. The Robertazzi estimator is very, very close to the average of RORA, which means the estimator is quite accurate. The other thing is, as I mentioned before, the max RORA is the worst case is still better than the canonical. A third thing to notice is that the analytical bound is 7 orders of magnitude greater than the worst case for ordering random association. So this shows that the analytical bound, the Wilkinson bound, can be not as useful. And I'm going to show also similar results for uniform -1, 1. The error is greater, right? We have the max being 10 to the -14 as opposed to 10 to the -15 here. we also have the analytical bound being 7 orders of magnitude worse than the actual bound. So now I'm going to talk about Neckbone, which is a case study where we're not just using generated values. So again, I'll describe the experimental setup. Neckbone is a computational fluid dynamics proxy app based on the NEC 500 physics simulation code. And what happens in Neckbone is it solves a 3-dimensional Poisson equation by running conjugate gradient and stopping at 101 iterations. Now this is nice for us because we can take the residual and measure evenly across different runs and different algorithms. What we're doing here, that on the x-axis we see various different all-reduce algorithms. These have all been implemented in the great project SimGrid, which we use and is from a different group of researchers in France. And they've implemented 16 all-reduce algorithms. You can see Intel's MPI, you can see OpenMPI, you can see MPitch, and others. So we can compare various different implementations to see how different results are. What we notice here is there are only 4 different results. Now, one of them is an outlier. We're still investigating. You see this SMP RSAG. What we have on the y-axis is the difference between the default, right? So default here is set to be 0. We don't know why the SMP RSAG is much better, has lower error, but this error did not appear by using different algorithms on a non-simulated architecture. So we suspect it is in the interaction of Neckbone and SimGrid. But regardless, let's look at some tabulation. These are all the 4 results across the 16 experiments. So there's a huge state space, but not that many different answers. And most only differ by the last few bits, right? So these 3 are all the same except for here. So that talks about Neckbone, the case study, and I'm going to talk a little bit about future work and then conclude the talk. So some future work that we find interesting would be to generate more realistic reduction trees, some realistic random input, and expose more non-determinism in SimGrid. This is because we want to see if we can get more of these answers that are permissible by the MPI standard. So in conclusion, we looked at error for 4 different families of reduction strategies. We noticed reduction tree shape or association has a greater effect than how the array is ordered. And we noticed that despite the large state space, realistic programs generate only a tiny subset of what is permitted. We also found, to a lesser extent, this happens with simulated input as well. So thank you everyone for your time. I have the source code and the slides available at the URL below. And thanks again.